Welcome to Foundation Mathematics, Simultaneous Equations, Linear Equations, Graphs, and Inequalities. The objectives for this session are to solve simultaneous linear equations using elimination, substitution, and graphs. We are also going to manipulate linear equations and solve linear inequalities using graphs. Let's begin with an example. A company prepares party bags for children's birthday parties. Suppose each party bag must contain 2 toy cars. Let P equal the number of party bags and let T equal the number of toy cars. Then we have the relationship T equals 2P. The value of T is dependent on P. An illustration of this is given as shown in the graph. The independent or explanatory variable is usually on the x-axis. So in this case, the number of party bags P is on the x-axis. And the dependent or response variable is usually on the y-axis. It reacts to changes in the independent variable. So in this example, the number of toy cars T is on the y-axis. Sometimes variables are related but do not have a cause-effect relationship. Let's now take a look at another example. Temperature is a numerical representation of how cold or hot an object is. Temperature is defined to be the degree of heat present in an object. For everyday applications, the basic unit of temperature is the Celsius scale, in which 0 degrees Celsius corresponds to the freezing point of water, and 100 degrees Celsius corresponds to the boiling point of water. It is often called the centigrade scale because the distance between these two is divided into 100 equal intervals. The second basic unit for measuring temperature is Fahrenheit. The freezing point of water on the Fahrenheit scale corresponds to 32 degrees Fahrenheit, and the boiling point of water corresponds to 212 degrees Fahrenheit. The distance between these two is divided into 180 equal intervals. To convert the Celsius scale temperature to Fahrenheit scale temperature, and vice versa, we can use this formula to convert from Fahrenheit to centigrade or Celsius, and this formula to convert from Fahrenheit to Celsius. As you can see, Fahrenheit and Celsius are related, but one does not depend on the other. The equation of a straight line or a linear line can be written as y equals mx plus c, where m is the gradient and c is the y-intercept. Let's take a look at another form of this equation. Suppose we have p equals ax plus by. Let's see how we can convert this into the form y equals mx plus c. We're going to begin by isolating the y's by subtracting ax. So here's the original equation, and here we're subtracting ax. To give us p minus ax equals by. We can now divide by b in order to give us y equals p minus ax all over b. So this can be written as y equals p over b minus a over b x, or y equals minus a over b x plus p over b. And so now if we compare this to y equals mx plus c, we have that m equals minus a over b, and c equals p over b. And therefore we've shown that p equals ax plus by is equivalent to an equation of the form y equals mx plus c. Now let's take a look at another example. We are required to write down the gradient and y-intercept of these equations. Y equals minus 8x plus 5 and 2x plus 8y equals 7. So let's solve part A first. We know that y equals minus 8x plus 5. This is already in the form y equals mx plus c. So the gradient m equals minus 8. And the intercept c equals 5. Now let's take a look at part B. We are required to write down the gradient and y-intercept of 2x plus 8y equals 7. So let's solve this. If we rearrange 2x plus 8y equals 7, so that y is the subject of the equation, we have that 8y equals minus 2x plus 7. Here we've subtracted 2x from both sides. Now we can divide by 8 to give us y equals minus 1 over 4x plus 7 over 8. The equation is now in the form y equals mx plus c, and therefore m equals minus 1 over 4 and c equals 7 over 8. Now let's take a look at another example. We are required to sketch y equals 5x plus 2. Clearly the line y equals 5x plus 2 is linear. So we find any 2 points on the graph and join them. The easiest 2 points to find are usually when x is 0, what's y, and when y is 0, what's x. So let's find out what's y when x is 0. We plug in the values in our line, as shown, to give us y equals 2. So when x is 0, y is 2. That's 1 point on our graph. And when y is 0, let's plug in our values. And rearrange. And finally, dividing by 5 gives us x equals minus 2 over 5. So the 2 points on the line are 0, 2 and minus 2/5, 0. We can plot these on our graph. 0, 2 is as shown, and minus 2/5, 0 is as shown. We simply join the points and we have our line. Now let's take a look at another example. We are required to sketch y equals 3 minus 2x. Pause the video and have a go. Press play when you're ready to view the solution. Y equals 3 minus 2x is linear. So find any 2 points on the graph and join them. The points we're considering again are when x is 0, what is y, and when y is 0, what is x. So let's consider x equals 0 first. So when x equals 0, plug in the values. And tidy up to give y equals 3. So one of our points is 0, 3. Now when y is 0, plug in the values again, as shown. Then rearrange to give 2x equals 3. And finally divide by 2 to give x equals 3 over 2. So the 2 points on the line are 0, 3 and 3 over 2, 0. As you can see, we've plotted both of these on our graph. We simply join the points and we have our line. Now let's take a look at another example. We are required to sketch x plus 3y equals 18. Pause the video and have a go. Press play when you're ready to view the solution. Again, x plus 3y is 18 is linear. We find any 2 points in the graph and join them to sketch our graph. When x equals 0, plug in the values in the equation. Rearrange to give 3y equals 18. And then divide by 3. Giving y equals 6. And now find the other point. When y is 0, again, plug in the values in the equation. And tidy up to give x equals 18. So the 2 points on our line are 0, 6 and 18, 0. Let's plot these points. 0, 6 goes here and 18, 0 goes here. We join the points and we have our line. Linear simultaneous equations in 2 unknowns can have exactly one set of values that will make a pair of equations true at the same time. Let's take a look at an example. The solution to the following pair of equations, which is shown on your screen, is x equals 1 and y equals 3. Let's check this by substituting the x value and the y value in one of the equations. So let's check. 3, the coefficient of x. 1, x equals 1. 2, the coefficient of y. And y equals 3. Does indeed equal 9. 3 times 1 plus 2 times 3 equals 9. So the left-hand side equals 9 and the right-hand side equals 9. We can also check in equation 2. X equals 1. 4 from the equation. Y equals 3. And 11 from the equation. The left-hand side equals 11. 1 minus 4 times 3. And the right-hand side equals 11 too. And therefore we've checked that x equals 1 and y equals 3 do indeed satisfy both equations. Let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. We are required to find the point of intersection of the equations shown on your screen using elimination. So what are the steps required to solve this? First, make the coefficients of x or y the same. Next, subtract the equations to eliminate x or y. Third, find the uneliminated variable. And finally, substitute into one of the original equations to find the eliminated variable. We will now proceed to solve part A. We must either make the coefficients of x the same or the coefficients of y the same. We will proceed to make the coefficients of x the same. Multiply equation 2 by 2 to give 10y equals 2x plus 48. So 2 times 5y is 10y. 2 times x is 2x and 2 times 24 is 48. Now subtract equation 1 from equation 2' to give 9y equals 0 times x plus 45. 10y minus y equals 9y. 2x minus 2x equals 0x. And 48 minus 3 equals 45. So dividing both sides by 9 gives y equals 5. Now substitute y equals 5 in equation 1 to give 5 equals 2x plus 3. Rearranging gives you 2x equals 2. And finally dividing by 2 gives x equals 1. Now check that y equals 5 and x equals 1 is correct when substituted into equation 2. Substitute y equals 5 and x equals 1 in equation 2. Now the left-hand side equals 25 and the right-hand side equals 25. So the left-hand side and the right-hand sides are equal. Therefore the check confirms that y equals 5 and x equals 1. We will now proceed to solve part B. We must either make the coefficients of x the same or the coefficients of y the same. We will proceed to make the coefficients of y the same. Multiply equation 1 by 3 to give 3y equals 9x minus 12. Now subtract equation 2 from equation 1'. 3y minus 3y equals 0y, 9x minus 2x equals 7x, and minus 12 minus minus 19 is plus 7. Next, find the uneliminated variable. So rearranging gives that 7x equals minus 7, and dividing both sides by 7 gives x equals minus 1. Now substitute into one of the original equations to find the eliminated variable. So substituting x equals minus 1 in equation 1 gives that y equals 3 times minus 1, the value of x, minus 4 equals minus 7. So we have the two values now. X equals minus 1 and y equals minus 7. Finally check that the values of x and y are correct in the other equation. So let's substitute these values in equation 2. So substituting x equals minus 1 and y equals minus 7 in the equation gives 3 times minus 7 equals 2 times minus 1 minus 19. Indeed, both sides are therefore equal. Left-hand side equals right-hand side equals minus 21. Now let's take a look at another example. We are required to solve the equations shown on your screen using substitution. So what are we required to do to solve these two equations by using substitution? Let's go through the steps. First, rearrange one equation so that one unknown is the subject of the equation. Next, substitute in the second equation. And finally, check by substituting the x and y values in the equations. So let's solve this example. We are going to make y the subject of the equation. So let's rearrange. First, we're going to make y positive, so we add y to both sides. Next, we subtract 3 so that y is isolated on one side. And now we substitute equation 1 dash in equation 2, as shown. And then tidying up gives us 5x plus 6x minus 6 equals 16. Then rearranging and tidying up gives us 11x, and 16 plus 6 is 22. Dividing through by 11 gives us x equals 2. Now we substitute x equals 2 in equation 1 dash. So y equals 3 times 2 minus 3. To give y equals 3. And therefore the solution is x equals 2, y equals 3. Let's now check that this is correct. So on the left-hand side, we have 3 times 2 minus 3. And of course, the right-hand side, we have 3 as well. So left-hand side equals 3, and right-hand side equals 3. And therefore, the two sides are equal. Now let's check in equation 2. 5 times 2 plus 2 times 3 equals 16. So the left-hand side equals 16 and the right-hand side equals 16. Therefore, x equals 2 and y equals 3 satisfy the given equations. If solutions of simultaneous equations exist, then they can be represented graphically. Solutions to a pair of simultaneous equations represent points of intersection of their graphs. Let's take a look at an example. On the same axes, draw the graphs x plus y equals 7 and 2x minus 3y equals minus 6. Using the graph, give the solutions. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. First, produce a sketch of the equations. On your screen, you have x plus y equals 7. Superimpose on this the line 2x minus 3y equals minus 6. The solution is x equals 3, y equals 4, as shown. If we substitute x equals 3 and y equals 4 in equation 1, on the left-hand side we obtain 3 plus 4, which equals 7. And as the right-hand side is 7 as well, we have that the left-hand side equals the right-hand side. Now let's check in the second equation. Substitute x equals 3 and y equals 4 in equation 2. So 2 times 3 from x equals 3 here, and 3 times 4 from y equals 4 here. And 2 times 3 minus 3 times 4 is minus 6. So the left-hand side equals minus 6, and of course the right-hand side equals minus 6 also. And therefore the solution does indeed work for the second equation as well. Let's now take a look at two special cases. Case 1. On the same axes, draw x plus y equals 3 and 2x plus 2y equals 6. Using the graph, give the solutions. So let's solve this. Here's the graph of x plus y equals 3. And on top of that is the graph of 2x plus 2y equals 6. As you can see, the two equations have the same line. So the number of solutions is infinite. Let's now take a look at case 2. On the same graph, we are required to draw x plus y equals 3 and x plus y equals 6. And then, using the graph, we are required to give the solutions. Again, let's solve this. Here's the graph of x plus y equals 3. And here's the graph of x plus y equals 6. As you can see, the two lines are parallel. And therefore, the number of solutions is 0. Let's now take a look at graph conventions. What is the difference between dotted and solid lines in a graph? So let's take a look at an example. Suppose this dotted line represents y equals f of x. The shaded region is y greater than f of x. And the unshaded region, or the region shaded white, is y less than f of x. Suppose instead we had a solid line for y equals f of x. Then the shaded region represents the area y greater than or equal to f of x. And the unshaded region, or the white region, represents y less than or equal to f of x. Take a look at this example. On graph paper, shade the region satisfying the inequalities x less than 4, y less than 3x plus 3, y greater than or equal to minus 3, and x greater than 0. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Begin by drawing the dotted line for x equals 4. Notice that we need to consider this because we are looking at the region x less than 4. Here we have another dotted line, y equals 3x plus 3. And again, we need to consider this because we need to consider y less than 3x plus 3. And now we have a solid line representing y equals minus 3. And notice we need to consider this because we're considering the region y greater than or equal to minus 3. So how do we know what to shade? If y is less than, then we shade below. If y is greater than, then we shade above. And how do we shade if there are restrictions on x? So if x is less than something, then shade to the left of, and if x is greater than something, then shade to the right of. So in this example, where x is less than 4, we have x less than 4 is shaded to the left of the line x equals 4. And going back to y, we have y less than 3x plus 3, so we shade below the line y equals 3x plus 3. So y greater than or equal to minus 3, and we've shaded above the line. And finally, for the region x greater than 0, we're going to shade to the right of the line x equals 0. But where do all these regions overlap? It's here. And this is where all these inequalities are satisfied. Let's check a random point in this region, 3, 0. Does it hold for the inequality x less than 4? For our random point x equal to 3, 3 is less than 4. Does it satisfy the inequality y less than 3x plus 3? X equals 3 and y equals 0. Y is less than, or 0 is less than, 3 times 3 plus 3. Does it hold for the inequality y greater than or equal to minus 3? Since y equals 0, 0 is indeed greater than or equal to minus 3. And finally, does it satisfy the constraint x greater than 0? X is equal to 3, and 3 is indeed greater than 0. So for this random point, certainly, all these inequalities are satisfied. This brings us to the end of this session. If you have understood its contents, you should be able to solve simultaneous linear equations using elimination, substitution, and graphs. You should also be able to manipulate linear equations and solve linear inequalities using graphs. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to it.